Number 2 is just the formula for dot product. Number 4 is orthogonal, aka perpendicular, aka normal, aka dot product is 0. Number 12, the dot product is 13. 54 is neither. Now this one was a little weird. The orthogonal part was hopefully obvious. How do you know whether or not it's parallel? In order to be parallel, it has to be a multiple of the original and going the same direction. If you guys had even just drawn these, couldn't you have gone over 3, up 15, and then left 1 and up 5 and been like, they're not parallel? You could have just drawn them. Or if this was a positive 1, positive 5, it actually would have been parallel, would have been in line with or at the same angle. So parallel would have been in the same angle. And they showed you the quick little clue of, hey, it's a multiple. So multiply this by 3 or divide this by 3. It would have been parallel if it had been positive. You can always draw a picture, though, and basically get the same idea. And then the only other even I gave you, I think, was 76, right? I gave you lots of odds to be able to check. Oh, 54. Where's 54? Oh, I just did 54. Thank you, thank you, thank you. Okay, let's zoom in. This is not very big. The final answer is 5,318 pounds. 5,318 pounds. Kyle, was this the one you were talking about? They didn't give you very much? The force was due to gravity. You guys can see that original vector that's right there. The force, remember, we're supposed to do force times distance to get work. The force is gravity. They did a unit vector along the hill using the incline. So they did magnitude times the cosine of angle, magnitude times the sine of angle, but they just did a unit vector. I'm trying to get the book open so we can peek at it. Does anybody have a question on 74? I'm just assuming you do. Can I see hands if you have a question on 74? Sorry, 76, my bad. 54. Okay. Let me pull it up really quickly. Yeah, it was a hard one. I totally agree. Really quickly, everybody's here today except for Aiden's still gone, right? Everyone else made it. Okay. As we're checking this out, number 65, you guys need to help me out really fast on directions. I'm sorry. What were the directions on this one? Are they orthogonal? Oh, the projection of u onto v or v onto u? U onto v, okay. So if we're trying to do projection, there's a formula for that, right? Of u onto v is equal to, I think we have the dot product, right? Over the magnitude of v squared times vector v. Oops, I left behind my fraction bar. All right, there we go. So the very first step to doing this one would have just been a dot product. And so my dot product would have been, just looking over here, you guys got negative 12 plus 12, right? What does that mean when your dot product is 0? Orthogonal, perpendicular, which means the projection is 0. Remember that example yesterday, how I was pulling straight up and saying, how is that adding to the forward motion? It's not. It's not. It's a very silly way of saying it. It's not a very physicsy way of saying it. But, yeah, it doesn't add to it at all. Projection 0, and you're done. Yeah. And then number 71 was the next one. Work. Ooh, there's a formula for that. Now, there are 2 different ways of doing this. But I think the easiest way, as much as is possible, force times distance. That's like a basic, you guys should have seen it in physical science, I think. Work equals force times distance, which in our context, we need a force vector and a distance, ultimately, vector. And then we can do a dot product and we'll have the work. What do you see over here? Force is V, and then what's PQ? Distance from P to Q is how much it was moved. So it's as easy in this one as just doing, well, hold on. Don't I need, I could do dot product of V and PQ, but I need to make PQ a vector, but that's not too bad, right? How do we make PQ into a vector? Good, final minus initial, and so 4 minus 0 is 4, 7 minus 0 is 7. Those are all formulas in section 6.3. How to do, or how to make a vector with an initial and a terminal point. It was in homework and we did it in class notes. So now all we have to do is a dot product. And guys, how do dot products work? Multiply the A's plus the B's. End up with 4 plus 28. Anybody double check me? 32 look good? Nice. Now that's the basic idea of work. But then number 76 got harder, right? 76 didn't seem to give you a lot. I know it's a horrible, and then the book was, it's okay. An SUV with a gross weight of, weight. Weight. We know that, right? Of 5,400 pounds is parked on a, so 5,400 pounds, is parked on a slope of 10 degrees. Assume that the only force to overcome is the force of gravity. Find the force required to keep the vehicle from rolling. What's it going to want to do? It's going to want to roll down the hill. Does that make sense? Hey, do you guys remember where we're allowed to put this 10 degrees? Right? Does this actually say work? Couldn't you technically just say opposite over hypotenuse if you knew your picture from section 6.3? Because this needs to be compensated for. I need to figure out what's trying to pull it down the hill so we know how much, basically how strong the brakes need to be from keeping it from going down that hill to overcome that force. So couldn't I just use sine? 10 degrees is equal to x over 5,400. Now hold on. You guys saw the answer key, and it was a whole lot harder, true? So let's check out what was going on with the answer key. The answer key said, hey, you got to think about this force and how it's only down and it's not right left. 0, 5,400, is that what my picture shows? Does my picture show 0 and 5,400? Yeah. So ultimately, you could say that that force is equal to 0 and negative 5,400. That's not wrong. It's 5,400 straight down with no right left. I agree with that. What else does this say? This also says the unit vector along the hill is cosine 10 degrees, sine 10 degrees. So then they said, okay, well, we could also talk about a little baby unit vector. Along the hill, which is parallel with this guy. And they said we could talk about the little unit vector as being cosine 10 degrees and sine 10 degrees. Okay, we could do that. We could talk about cosine 10 degrees, sine 10 degrees. The little baby unit vector being this little guy right here. And then they said, now just take a unit vector, unit vector. Now go ahead and do the projection, which would be the dot product all over the magnitude squared times the vector, which ends up being, since this is a unit vector, 0 times cosine, and what ends up happening here? The 5,400 gets multiplied by the sine. The 5,400 gets multiplied by the sine. And so what they said is that the magnitude of the force is the 937.7, which is exactly what we would have found. We didn't end up making gravity negative because we were trying to overcome. We just made it a positive. So we're going to actually work out okay. If we had made it a negative, like gravity technically probably should have been, because it is pulling downwards. Then we would have said, okay, well, this is a negative force. To overcome that, I need to go the opposite direction. So we could say x is equal to, thank you, ma'am. Instead of a negative 937.7, we would have gotten a positive 937.7. So we would have gotten that just from the picture, no big deal. The question is, how did they use it? So this picture actually made this work a whole lot easier. Instead of having to do the dot product, you could have just solved your little baby right triangle. But then they used that. They used the pounds required to keep the vehicle from rolling down the hill to go ahead and find the force. So the problem was in the question, it actually asked for, this would have been pounds. There you go. Find the force perpendicular to the hill. This is the first answer without having to do any dot products, without having to form any vectors, without having to do any projection. We just solved the right triangle. So much easier. But that wasn't the only thing they asked for. What was the other thing they asked for? Wait. Isn't that just this one? Oh. I didn't have to use all that crazy stuff from the answer key at all. I mean, kind of. I just had to use my picture from section 6.3. Has anyone at this point gone back in their notes and made a little star by the picture of the thing on a slope in section 6.3? If not, you better do it because it's going to be nice and helpful for the test. I'm not saying this specific hard example will be on there, but you've seen that it's useful in at least 2 different homework problems. Hint, hint, hint. The object on a hill with a little triangle from section 6.3. I think it was the last thing that we did. Let's see. So to find y, you could just do Pythagorean theorem. Square root of negative 5,400 squared plus 37.7 squared. And that's how you guys ended up with your final answer of 5,318 approximately. Does the book always do it the easiest way? No. This one, all you needed was your little baby right triangle in the picture. Kim, you were asking which one. I can show you really quickly. It was the end of section 6.3, this picture. Yeah. If anybody else wants a picture, go ahead. Real quick, Tony. Oh, I think it's for universal stuff. Oh, this one. You can leave just a couple minutes early to go to Richmond. Oh, maybe not. This is different. Need your permission slips. Okay, section 6.5. We covered your guys' questions. Let's go talk about section 6.5, whose math is almost easy. At the very end, it gets a little tricky. Here we go. Complex numbers. Why on earth are we talking about them? Because a complex number can be graphed. What? No. Complex zeros never showed up on the graph. Complex numbers never show up on a real graph. But we can graph complex numbers on their own special axis where we make the reals similar to the x-axis and the imaginaries on the y-axis. There is a way of graphing complex numbers. Not that we necessarily will have to apply beyond this section this year, but there is a method to trying to visually compare, contrast, etc. complex numbers. And how this works is that you're going to literally go over A and up B. So this is going to be similar to a horizontal coordinate, like an x coordinate, and the B is going to be the vertical coordinate. So when you guys have this example right here, 3, negative 2i, guess what? Now what did I not put on the end? No arrow. But besides that, isn't it a lot like a vector? With a horizontal component and a vertical component? You can graph a complex number on a special coordinate axis where we put the real component as the horizontal and the imaginary component as the vertical. So 3, negative 2 was how far over the real part and how far down the imaginary part we went. Gavin? Because it's not a vector. Like there's no direction to this. Does that make sense? Yeah. So it's similar to a vector in the sense that you have a horizontal, vertical, but there's no need for an arrow because it's not showing, signifying any force, any direction. But it still has a magnitude. Hey, it still has a magnitude. Check it. The magnitude of a complex number isn't called magnitude. It's called the absolute value. Wait, isn't absolute value the how muchness to a number? It's the distance from a number on a number line to 0. It's the how muchness. -5 has a how muchness of 5, like that's its magnitude. So technically it kind of has the same meaning, but it's not going to be with the double lines like a vector was. So whenever you're trying to find the absolute value of a complex number, it's possible. It's just going to be super, 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 super weird because it's actually Pythagorean theorem, like magnitude. So maybe there's not really a lot of memorizing formulas for section 6.5. Maybe it's more understanding how they relate and already having the formulas from the vectors from 6.3 and 4. So, kiddos, for this example down below, pause. I want you to put a quick little pat on everyone's shoulder in your group really quickly. A super non-awkward but trying to wake everybody up sort of way. Pat everyone on the shoulder. Just give me a quick pat in the back. Quick little pat. You're just checking in. Everyone's awake. All right. There we go. So, guys, what quadrant is number 6 in? Over 5, down 12. Are we okay? How do we find the absolute value then? Adam's saying it. Think 5, think -12. The absolute value is that. All we have to do is Pythag. So we're going to have 25 plus 144, which ends up equaling 169, which is 13. Yeah. But before this section, would you have had any idea that the absolute value of a complex number is just an hypotenuse? That doesn't make sense, does it? Unless you think graphically about, a complex number is really kind of like a vector in the sense of horizontal, vertical. So a Pythagorean theorem kind of makes sense. So yeah, it's 5, 12, 13. Good, Kyle. Ready? So wait a minute. There's another way of writing a complex number? The answer is yes. There's another way of writing a complex number, and the answer is yes. There is another way of writing a complex number. If I were you, isn't your highlighter, your color pen somewhere close? You might want to highlight color pen this, because it's just weird. We've been using this form. You've been using this form ever since Algebra 2. A plus BI. You've been using, we did it more this year, but you've been using the standard form for a long time. There's a trig form. Yes, which has different applications. Once again, it's nice. We're not going to have to apply it beyond this section at all. Remember, pre-calculus is pre-everything future math. We're just kind of introducing you to a lot, which makes it kind of hard sometimes. But the reason why we can do a trig form is basically built on magnitude cosine theta and magnitude sine theta, which was a thing with vectors. It was how you got component form given a magnitude and direction. Check it. Isn't it just magnitude cosine theta, magnitude sine theta? Because r, which is the same thing as the absolute value of a plus bi, is just going to be the square root of a squared plus b squared. Theta is just going to be tangent inverse of b over a. Oh my goodness, these formulas are going to be on your card from 6364. You're just going to have to know how to use them for complex numbers. A is going to equal, she's back. A is going to be r cosine theta because it's the adjacent side. B is going to be r sine theta because it's the opposite side. These are all vector formulas, just being applied to complex numbers. So when we get down here and when we have 1 minus root 3i, more permission slips. represent it graphically. Guys, isn't that in the fourth quadrant again? Over 1 and down somewhere like here-ish, right? Write the trig form. Aw, stink. Aren't we going to have to find r? Isn't that just Pythag? 1 squared plus root 3 squared. Wait a minute. Isn't that 1 plus 3 is 4, and square root of 4 is... Oh my goodness, maybe I should have known that this is a 1, 2, root 3 triangle. 30, 60, 90 from geometry. Wait, what's my angle going to be? Hold on. Who has a tangent of negative root 3 over 1 in the fourth quadrant? Square root of 3, not 30. 1, not 45. Root 3, square root of 3 over 3, 1 square root of 3. This is a 60 degree in the fourth quadrant. So I could write this a couple different ways. Long story short, in complex number form, real short for theta, we don't want negative angles. No, because it's just going to be awkward in this form if you write negative angles. So our trig form is going to end up being not negative 60 degrees, which is what your calculator would tell you, but instead positive 300 degrees. So then my trig form is going to be z, I know it's weird, equals 2 cosine 300 plus I sine 300. I know it's weird, but it's right. And you're not simplifying that. If you did simplify that, you get way back, or all the way back to 1 minus root 3I. So in a sense, you're saying, where did you come from? Oh, you came from here? Yeah, came from there. There is another way of writing it, which our book doesn't really talk about. It's r cis theta. It's just a shortcut form. So technically, other books might write this as z equals r cis 300, which would mean cosine 300 plus I sine 300, but we don't use that. We just use the actual what it really is, because some people get really confused by that one, and I don't know exactly why, but our book chose not to go that far. That one's kind of rough, but you just need to plug into your r cosine theta, r sine theta, or go back to an r cosine theta, r sine theta form, using Pythagorean, using tangent inverse. But what are you going to do if they ask you to go the other way? They say, hey, here's the trig form. Go to the standard form. Go to the a plus bi form. Oh, wait. Doesn't that just mean that we actually do it? Like we actually do 5 times cosine of 135? And we actually do like 5 sine 135? Is it really that easy? Yeah. Now, bad news. It's a unit circle value that you guys should be able to use or dig up from your memory what cosine and sine is to plug in. Good news, the test on Friday, you're allowed to use your calculator for the whole thing. So I guess even though you should know this, technically you could go ahead and plug it into your calculator and have it as well. Except, ooh, in the second quadrant, isn't the cosine negative? So you're going to end up with z is equal to negative 5 root 2 over 2 plus 5 root 2 over 2I. And you can always double check you got it right, because a negative x and a positive y better land you at where you think it is. Ah, it does. So going forwards isn't too bad. It's just unit circle or plugging into your calculator. Going backwards is a little bit hard, but if you use the formulas, you're okay. Just be careful to always keep your thetas positive and look at the picture. Because if you had done tangent inverse of this guy, it would have given you negative 60, which would have been the exact same thing it would have given you if it had been negative 1 plus root 3I. But negative 1 plus root 3i would have landed you in a totally different quadrant. Negative 1 plus root 3 would have landed you in this quadrant up here. And negative 60 wouldn't have been sufficient. You would have needed to go ahead and make sure that you figured out that was 120 degrees. Your calculator sometimes with tangent inverse gives you the wrong quadrant, and you have to add 180 to get to the right quadrant, which is why I always say draw a picture first. That way you can compare the angle to the picture and make sure you have the right one. So here's where the section ends. The section ends with, okay, now you've learned that there are these ways of writing complex numbers using trig. There are these ways of writing complex numbers using trig. Which seems really weird unless you realize that a complex number is really can be represented by a right triangle, and then you're like, okay, well, I guess I can get where trig comes from. So the rest of this section is basically like, okay, if you ever see complex numbers in trig form, there are ways of playing with them. There are operations that can be done with them. There are ways of playing with them, operations that can be done with them. You know what? Let's make life easier. This is our first test. It's going to determine our grade. You're allowed to do formulas on your card from 6.3, 6.4, or 6.5. I forgot about these ones at the end. You're allowed to do formulas on your card from everything but law of sines, law of cosines. Sound good? Including the area formulas. You're not allowed to do those. But 6.1, 6.2, off the table. Everything else on the table as far as what to use. Cool? Cool. AKA, highlight these and put them on your card. This says, you're given two complex numbers. They're both in trig form. Multiply. Ugh, that would have been awful. That would have been horrible. Because you would have had to distribute the R, and then FOIL. Ugh. But based on trig identities from last chapter, if we had done all of that hard work, and with an old book I actually would have done the hard work and shown you where these formulas came from, because these were emphasized a bit more. If you really did distribute the R's and FOIL it all out, you would actually end up with cosine sine. You would end up with cosine of A plus B, the sum and difference formula. And you would end up with sine, cosine sine with I's, which were condensed or could be condensed to this. So if you just memorize the pattern, it's actually really easy and you don't have to FOIL. If they ever ask you to multiply two complex numbers like they're doing down here, you can say, I have formulas for that. And every time the formulas say, do the operations to the R's, do the operations to the R's, but the multiplication becomes addition of thetas, division becomes subtraction of thetas, and we'll see what happens when we try to raise a complex number to a power on the next page. But for right now, do the operation to the R's. Okay. Well, the operation to the R's is going to be 2 times 6 is 12. So if this is Z1 and this is Z2, two complex numbers, I see them, they're in that trig form. Z1 times Z2 is going to equal 12 times. Multiply the R's. 2 times 6 is 12. Easy. What am I going to do to my thetas? I have space. I need to get my thetas. What am I going to do with my pi over 4 and pi over 12 if I'm multiplying? Yeah. So if I need to add them, I think I need to get a common denominator, right? But what's 3 pi over 12 plus 1 pi over 12? 4 pi over 12, which is the same thing as pi over 3. Now, if they wanted me to do standard form, I could keep going. I could find the unit circle equivalent and multiply by 12. But didn't they say leave it in trig form? Ha 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 ha. Follow the formula. 5-minute bells are ringing today. I don't know why. So what about division? Division says, hey, you have two different complex numbers. There's one. There's another one. divide the r's, do the operation to the r's. Check out your formula. What do you do to the thetas? Oh, this is actually kind of easy because they're decimals. Go figure. Since when do we say this is easy? There are decimals in pre-cal. But what's 4.3 minus 2.1? 2.2. Which is so much easier than what we would have had to do if we were trying to actually do this by hand, multiplying by conjugates and using properties, and oh, that would have been awful. That one's nasty to prove. This page says if you have two complex numbers being multiplied or being divided, is there a simpler way than foiling it all out, figuring it all out? And the answer is yes. They're pretty nifty tricks, and they all come from trig identities that we're not going to see: the why, the how, the wherefore. I'm just curious if you can plug in properly, correctly, and identify it, which is why I'm letting you put these formulas on your card. There is one last operation to do with complex numbers. How to raise a complex number to a power. How to raise a complex number to a power. Now, I'm not going to walk through where this property comes from. Some years I do. Instead, I'm just going to actually go backwards from the property and just show you how it works in this example. So if we were trying to square a complex number, this could be like a z1, a z that's being squared. I don't even need to call it z1. There's only one complex number up here. Well, let's call him z. So we could think about this as squaring z. How do I do that? Well, do the operation to the r. So r is going to end up being squared. And cosine is going to take that 2 and be like, oh, sweet, 2 theta plus I sine 2 theta. Cosine 2 theta plus I sine 2 theta, which are double angles and which we could do, etc., if we needed to. This theorem, de Moivre's theorem, is super easy as long as n is greater than 1. If any power squared, cube, 4th power, 5th power, 6th power, it's so easy. Because in order to take this and to say, oh, hey, I'm raising a complex number to the 4th power, 3 is going to be to the 4th power. Whatever the r is to the 4th power. Then the angle just says multiply me by the power. So 60 times 4 is 240 plus I sine of 240. Doesn't seem any harder than the page before, and that's always going to be true for n greater than 1. That's always going to be true for n greater than 1. There is something, though, at the very end of homework that's going to get a little tricky, a little funny, a little weird. Because do powers always have to be greater than 1? An example of a power that is less than 1? An example of a power that's less than 1 would be like 1/2. Or 1/3. Or 1/4. So kiddos, at the very end of homework, you're going to have this weird example. Or maybe a couple weird problems that you're going to need to go look at examples in the book. I think I'll post in your Google Classroom, just as like a comment on this homework, I'll post a link to last year's video where we did do some of these examples. Tony, go ahead and go to Richmond if you haven't yet been. I bet that's what it is. Tony? He's on his way. Bye. That's on the video. For you guys to try to do this, but here's a good piece of advice. This isn't on the test. The fractional part is not on the test. We'll see it. We'll play with it a little bit. We'll finish homework questions that you guys might have on it tomorrow. See what you can do, because the bell's about to ring. On the fractional ones, you kind of do this, but I want you to do this with the fractional ones and then be like, wait, but the back of the book has something extra, has something more, and it has to do with when we cut down angles. What used to fit in 360, well, the door might have been open for a few more answers to sneak in. But we'll see that tomorrow. All right, cool kids. You know what to do, right? All of homework, do your best on the fractional de Moivre's ones. Feel free to submit even without totally getting those very last couple on the fractional powers.